Welcome, ladies and gentlemen. May I have your attention, please? Thank you. Let's go ahead and take a look at our Bellwork responses today. These equations look similar, and yet you'll be following a distinctly different solving equations recipe as you work to find the value of x. And so let's go ahead and take a look at number one. Remember our strategy. If x appears just on one side of the equation, right, and not in the bottom of a fraction, we could go ahead and cover up the equation and just focus in on the left-hand expression that involves x. So that's my forward steps. If I were to plug in something for x, a variable value, and evaluate that expression in accordance with my order of operations, the first thing we would do is square the value of x, and then multiply by 2, and then lastly subtract 3. So to reverse and undo those forward steps, to get our solving steps, we could, let's see, undo that subtraction by addition of 3, and then divide by 2, and lastly, what undoes squaring? Well, considering the positive and negative square root. Let's go ahead and apply those solving steps now to both sides. So we'll first go ahead in that red solving step, add 3 to both sides. That yields 2x squared equals 52. Next solving step in red is to divide both sides by 2. So we'll divide both sides by 2. That isolates the x squared term. And we get 26. And then lastly, we can undo the squaring by considering the positive and negative square root. That is to say, if x squared equals 26, then x must equal the positive and negative square root of 26, right? Now, sometimes that radical will reduce, sometimes it won't. In this case, it doesn't, but I do have two different answers, right? One is x equals the positive square root of 26, and one is x equals the negative square root of 26. Let's go ahead and take a look at our different question, number 2. There's the same terms here, and yet it's a distinctly different order of operations. So again, x only appears once. It's not in the bottom of a fraction, so we could cover up the equation and focus in on the expression containing my variable. If I were to substitute in a variable value for x and evaluate, our first thing in our forward steps would be times 2, times 2. Then we would subtract 3. And lastly, we would square. So to get our solving steps, we'll simply reverse and undo our forward steps. This time, our first solving step is going to be undoing that squaring. And so now my first solving step is take the positive and negative square root to undo the squaring. Then we'll add 3 and lastly divide by 2. Let's go ahead and apply those solving steps in order. So when we take the positive and negative square root to undo the squaring, we get quantity 2x minus 3 alone, but that's equal to the positive and negative square root of 49. Sometimes this will reduce, sometimes this radical won't. But in either case, in my solving steps, we're going to split it up into 2 separate paths now, just like we did in our early activity in Unit 1. In one path, the quantity 2x minus 3 is equal to the positive square root of 49. That is positive 7. In the other path, 2x minus 3 is equal to the opposite square root of 49. That's negative 7. Now we'll continue on with our solving steps. That is, add 3 to both sides. Just we're doing it to both the equations now as we follow along in each path. And so once again, plus 3 to both equations. Go gadget arm. 2x equals 10 on the left. On the right path, 2x equals negative 4. Divide both sides by 2 to finish it out. And it looks as though x equals 5 or x equals negative 2. Remember, these are just potential solution values. I'm going to go ahead and check this negative 2 in the original, follow my forward steps. Negative 2 in for x. I get 2 times negative 2 is negative 4, minus 3 is negative 7. Quantity squared is positive 49, so by golly, that works, and the same is true for x equals 5. In this way, we see that depending upon your order of operations in your original equation, you'll get very different results. And that's the beauty of creating a recipe of solving steps for success. All right, let's go ahead and take a look at our introduction to polynomials discussion for the day. A polynomial is just a collection of variable terms where my x terms all have whole number exponents. And so we've seen polynomials. They have the form a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus a sub, well, that looks like an alphabet's nightmare. But I want you to know a polynomial just looks like a collection of powers of x terms added or subtracted together. Sometimes there's only one term, sometimes there's 12 terms. But in each case, if there's a variable term, it's raised to a whole number exponent, like 0, 1, 2, 3, and so on and so forth. If there's a fractional exponent, then it's not a polynomial. If there's a negative exponent, then it's not a polynomial. This particular expression, go ahead and write it down on the right side of your page. Negative 2x to the fifth plus 4x cubed plus 8x minus 11 is an example of a polynomial. This particular polynomial is in standard form because standard form arranges the exponents in decreasing order. Go ahead and write that on your note sheet, please. So standard form is our first blank. It arranges exponents in decreasing order. That is, I have the highest exponent first. The highest exponent in this polynomial is an exponent of 5. That comes first, and then decreasing order. So if cubed is the next highest exponent, that'll come second. There's an x to the first term here, and then a constant term. So we want to make sure that you're putting the highest exponent term first when we're writing in standard form. The coefficients are the multipliers on the variables. As I look at this particular polynomial, I see that negative 2 is a coefficient, 4 is a coefficient, it's a multiplier on the variable term, 8 is a coefficient, it's a multiplier on the variable term, and so if we listed those, we have negative 2 is one coefficient, positive 4 is one coefficient, and 8 is another coefficient. They're the multipliers on the variable terms. The leading coefficient is the coefficient that appears on the highest degree exponent. In this case, my highest exponent was x to the fifth. That term, right, that term gives the leading coefficient of negative 2. So we've already seen that negative 2 is a coefficient because it's on the highest degree term, the highest exponent term. It's also the leading coefficient. And lastly, the constant term does not have a variable multiplier. In this case, the constant is negative 11, right? It's the one that doesn't have a variable multiplier on it. It's also, in standard form, that constant term is also the y-intercept of the graph. 0, comma, negative 11 would be on the function y equals negative 2x to the fifth plus 4x cubed plus 8x minus 11. That's for you. Some polynomials get their own special name. When we see polynomials very frequently, sometimes we give them a shortcut name. And so we don't have to have these memorized necessarily, but we will be using the terms, and so you should know that a linear polynomial is just an x to the first polynomial versus a quadratic. A quadratic polynomial is a x squared. An x squared polynomial is the highest degree exponent. A quadratic polynomial may or may not include this x term or a constant term. However, the fact that it's an x squared as my highest exponent, that is what makes it a quadratic polynomial. A cubic polynomial has a x cubed as its highest exponent. And so a cubic polynomial has an x cubed. It may or may not have these other terms. It might not have an x squared term at all, or it might not have an x term at all, but if it has a cubed term is the highest exponent, then it's a cubic polynomial. Quartic and quintic aren't seen as much, but we'll definitely be using the terms linear, quadratic, and cubic frequently, so please make sure that those are first degree, second degree, and third degree polynomials. All right, so today we're going to be adding and subtracting and multiplying polynomials. First up, we can only combine like terms when adding or subtracting polynomials if the variables and variables exponents match exactly. So in order to combine like terms through addition or subtraction, the variable components have to match exactly. We add the coefficients of like terms and the variable stays the same. So when you add apples, you still have apples. When you add oranges to oranges, you still have oranges. The only thing that changes is how many of them you have. And the exponents of the variables do not change. So let's go ahead and check number 1. So 3x squared plus another x squared. These are like terms because they're both x to the second power, so I can combine them through addition or subtraction, and the result is 4x squared. Take a look at the second one. In number 2, 5yx squared plus y squared x squared. These are not like terms because this yx squared term, right? This yx squared term and this y squared x term don't have the same exponents on each of the variables. And so they both have y's and x's, but they're not like terms because that first term, 5yx squared, doesn't have a y squared. So I cannot combine it through addition and subtraction. If the second term had just had y to the first x squared, then I could combine them because they would match, but right now they don't. So this is fully simplified. This won't simplify any further through addition or subtraction. Number 3, are these like terms? Well, it turns out that this x squared z term and this zx squared term are like terms because they're both x to the second power and z to the first power. Order doesn't matter. That is, z times x squared is the same as x squared times z, so guess what? You can combine number 3. This would equal 6x squared z's because the exponents on those variables do match. So they are like terms. Go ahead and try 6y squared minus 4y squared and 7xy minus 6x squared y. Okay, so Ben found that 6y squared minus 4y squared, these are like terms because the y term both has the same exponent, so I can combine them through addition or subtraction. The result is 2y squared, 2y squared. And in the second problem, 7xy minus 6x squared y, the variable components do not match exactly. This first term does not have x to the second, and the second term does have x to the second, so guess what? This is fully reduced. That's fully simplified. We cannot combine those terms through addition or subtraction. Now let's go ahead and switch gears to multiplication. So when multiplying, it doesn't matter if the different factors in my product have like terms or not. We can multiply any term times another term. So we follow our distributive property if there's parentheses. We multiply coefficients, and we use the definition of exponents to determine the resulting exponent for a variable. In other words, we do the same thing that we did back in Unit 3. An x times an x is an x squared. An x squared times an x squared is an x to the 1, 2, 3, 4. An x cubed times x squared is x to the 5th. We add exponents when we multiply powers together with like bases. So let's go ahead and do the first one. 3x squared times 1x squared is 3x to the 4th. So we multiply coefficients and we add exponents together when we multiply powers with like bases. 5yx squared times y squared x squared looks like we get 5 times, and then x squared times x squared is x to the 4th, and y times y squared is y to the 3rd. And so we're adding exponents when we multiply together powers with like bases. I'm going to go ahead and scooch that down so we can box that. Number 3, 2x squared z times 4zx squared. We'll go ahead and multiply. We'll multiply the 2 times the 4. We'll get 8. X squared times x squared is x to the 4th again, and z times z is z to the 2nd. And so again, when we multiply powers together with like bases, our shortcut operation with the exponents is addition. Go ahead and try number 4 then, and number 5. Okay, so as you're multiplying these terms together, negative times a positive overall then is a negative. 6 times 4 is 24, y to the 4th power. So we'll go gadget arm. Negative 24y to the 4th power is the product in number 4. Number 5, I also asked you to try. That would be positive times negative is negative 42, x to the 1, 2, 3, x cubed, y squared. Notice how we're adding those exponents on the variable terms when we multiply them. And lastly, distributive property. So take a look at number 6, everyone. We're going to take this outside factor, negative 2x squared, and multiply it through the parentheses, term by term, like a distributive property problem from middle school. So here we go. Negative 2x squared times x cubed is negative 2x to the 5th. Remember, we add exponents. Negative 2x squared times negative 3x is plus 6x cubed. And lastly, negative 2x squared times a positive 1 is negative 2x squared. In this way, we can distribute that outside factor through my parentheses in accordance with the distributive property. All right, so we've got addition of polynomials. We've got multiplication of polynomials. Let's go ahead and add subtraction of polynomials. And so keep in mind, if we're subtracting two polynomials, this negative sign could be thought of as a -1. And it applies to everybody in this second set of parentheses. And so we can think about rewriting without parentheses. We would have to distribute that -1 all the way through. And so my first polynomial remains 2x squared plus 3x plus 8. And then my second polynomial, when I distribute the negative through, becomes -x squared minus 5x plus 1. Does everybody see where the sign change comes from? We're applying that negative to every single term in that second set of parentheses. So everybody's sign changes. Now we can go ahead and combine like terms. And so let's go ahead and find a pair of like terms. So what's one pair of like terms? Ben? Yes, that's correct. 2x squared minus 1x squared. Those are like terms because the variable component matches exactly. So we can go ahead and combine those and rewrite it as 1x squared, right? 2x squared minus 1x squared is 1x squared. Another pair of like terms? Yes, that's correct. Plus 3x minus 5x. Those are like terms, so we'll combine those as -2x. And then lastly, plus 8 plus 1 plus 9. So it looks like my final pairing of like terms, the plus 8, the plus 1 is plus 9. So my final answer will be given by x squared minus 2x plus 9. If we have a coefficient of 1 on a variable, we don't have to write it. So we don't have to write that coefficient of 1. And then we'll box our final answer. In number 2, right, before we can find the missing polynomial, like you'll have to do in your worksheet assignment in a little bit, it's going to be useful to first distribute through the parentheses to see the magnitude of each of these terms, so I can decide what must be added in order to get to my end result. That is 7x squared, 6x's, and then minus 10 for my constant term. So let's go ahead and multiply through. In the first polynomial, we get 3x squared plus 12x minus 6. And now I need to figure out what we need to add to this in order to get to 7, in order to get to 7x squared. Well, 3x squared plus how many x squareds equal 7x squared? Oh gosh, we need 4 more x squareds, so that 3x squared in green plus 4x squared in green equals my green 7x squared. What about our x terms? Well, our x terms, we have 12x's, but we end up with 6x's. So how we get from 12x's to 6x's? Well, we must have had a -6x term in that second polynomial, because now 12x minus 6x equals positive 6x in my final answer. Lastly, we've got our squiggle black underline -6, and we need to end up with -10. So let's see, from -6 I must subtract another 4 in order to get to -10. Now we've got 3x squared plus 4x squared equals 7x squared, check. 12x minus 6x equals positive 6x, and then lastly, -6 minus 4 equals -10. So we found the missing polynomial. Great. Let's go ahead and take a look at number 3. In number 3, we have a monomial factor. That just means a single term polynomial chilling on the back side of that sum or difference polynomial. And so we can still distribute that through, just like we did in middle school. It's just that now we'll be multiplying from the right side. So it still applies to every term, and we'll go ahead and multiply that through in order. So here we go. First term, -7x times 2x to the 4th would be -14x to the 5th. And then -7x times positive 3x cubed is -21x to the 4th. And then -7x times -x is plus 7x squared. And lastly, -7x times 4 is -28x. Take a look and make sure that we can't combine any like terms. Are we in standard form? Luke? Yes, we are in standard form. Thank you. Because the highest degree exponent is first. We'll go ahead and box that. So we've got our highest degree exponent first, that 5th, and then descending order. Looks like we already have an equal sign up there, so we can erase that. All right, let's go ahead and try number 4. And number 4, we're going to take this outside factor. We're going to take this outside factor, negative 3k squared m, and distribute it through my parentheses term by term. When we do so, we want to make sure that we're watching our signs and our variable exponents. So here we go. Negative 3k squared m times 2k cubed m. Here we go. Negative 3 times 2 is negative 6k to the 5th power m to the 2nd power. Next term, negative 3k squared m times the negative 4k m squared. Overall negative times the negative is a positive 12k to the 3rd m to the 3rd. Next, negative 3k squared m times a positive 7k m is overall negative 21k to the 3rd m to the 2nd. And finally, negative 3k squared m times negative k is just a positive 3k cubed m. Put it all together. And we've got our resulting polynomial. Okay, so we've added, we've subtracted, we've found the missing polynomial, and we've multiplied. That's printable for you. Now we're going to go ahead and practice taking two binomials and multiplying them together. This is one of the most common things we'll see coming up in our quadratic equations unit in Unit 6. When we take a look at quadratic functions, that's our first unit after second semester begins. Let's go ahead and take a look at our first product here. When we multiply two terms, it's kind of like a double distributive property problem. So the first thing we'll do is take this first factor in that first binomial, and we're going to distribute it through the parentheses. So all the way through, we'll multiply first. We'll kind of cover up that plus 3, and we'll multiply x times x is x squared. And then x times a positive 4 is plus 4x. And so we've just taken this x term in the first binomial, and we've distributed to each of those terms in that second binomial. Now we'll go ahead and cover up that first x term and focus on this blue double underlined 3. We'll distribute that through the second binomial so that it multiplies each term. Ready? Let's try. 3 times x is plus 3x. And then 3 times 4 is plus 12. So notice how my x term is multiplied all the way through the second polynomial. My 3 is multiplied all the way through the second polynomial, and now we can combine like terms. And so do we have any like terms? Why, yes, we do. We can combine the 4x plus 3x is plus 7x, and then plus 12 is my constant. We can make this look just a little bit better. Okay, we can do the same thing in number 6. So first, we'll cover up that minus 2 and focus in just on the x term. Let's distribute the x through that second binomial. Here we go. X times x is x squared. X times a plus 5 is plus 5x. Now we'll focus in on the negative 2. So let's take this negative 2. Remember that negative sign belongs to somebody. Does it belong to the x term in green, or does it belong to the 2? Well, the negative belongs to the 2. So we're going to count it as we distribute through each of these terms in the second binomial. So here we go. Negative 2 times x is minus 2x. Negative 2 times 5 is negative 10. Now I've distributed each of those terms in my first binomial through the second binomial, and we're ready to combine like terms. So what pair of like terms do we have, Caitlin? That's correct. We've got 5x and minus 2x, so my final answer is x squared plus 3x minus 10. And we're in standard form, so we'll go ahead and box it. All right, what happens when our polynomials match? Well, we'll do the same exact thing. We'll focus in on the first term in that first binomial, in this case x, and we'll distribute it through. X times x is x squared. Now we'll do some new colors. So x times 3 is plus 3x. Next, we'll focus in on the 3. 3 times x is plus 3x. And lastly, 3 times 3 is plus 9. Combine like terms. X squared plus 6x plus 9. And I want you to know that number 8, don't be fooled, this does not equal x squared minus 4. We cannot distribute this exponent through that sum or difference in the base x minus 2. X minus 2, quantity squared, means x minus 2 times itself. And so the first thing I do is I rewrite it so it looks just like number 7. X minus 2 quantity squared is equal to, you guessed it, x minus 2 times itself, x minus 2. In this way, we can go ahead and treat it just like number 7. X times x is x squared. X times negative 2 is minus 2x. Then negative 2 times x is negative 2x. And lastly, negative 2 times negative 2 is plus 4. And so we're multiplying two binomials together in number 8, just like we did in number 7. And now we'll combine like terms. It looks like we've got negative 2x when combined with negative 2x gives me negative 4x and then plus 4. Okay. So those are printables for you, and that brings us to our closure. So we can perform the indicated operation. We know that 3x plus 5x can only be combined through addition if their variable term matches exactly. Are these like terms in number 1? Yes, they certainly are, because they're both x to the 5th, so the result will be 8x. We add coefficients and we keep the variable the same. We don't change the variable term at all. In the second problem, we're multiplying. It doesn't matter if they're like terms or not. 3x times 5x is 15x squared. We multiply coefficients, and we add exponents when we multiply powers together with like bases. Number 3, we'll distribute this negative through the second set of parentheses. And so my first step would be to rewrite 4x plus 5 minus x minus 3. So to make sure you know where this subtraction came from, we distributed the negative through that second polynomial. And then the result allows us to combine like terms. 4x minus 1x is 3x. Plus 5 minus 3 is plus 2. So my final answer is 3x plus 2. We can multiply number 4. We can multiply 4x through the second polynomial. So we'll do 4x times x is 4x squared. We'll do 4x times positive 3 is plus 12x. We'll do positive 5 times x is plus 5x. And lastly, positive 5 times positive 3 is plus 15. Everybody consider, are there like terms in number 4? Are there like terms? Yes, again, it looks like this middle pairing. So my final answer would be 4x squared plus 17x plus 15. Go gadget arm, we'll scooch this down just a touch. And our final answer then is in standard form. All right, everybody look. Go ahead and tell your partner which of these problems, 1, 2, 3, or 4, resulted in quadratic polynomials as the final answer. So which of these problems, 1, 2, 3, or 4, resulted in quadratic polynomials? Go ahead and tell your partner. And yes, that's right, a quadratic polynomial means the highest exponent term is a squaring term. So it looks like our 15x squared from number 2, our 15x squared from number 2 is a quadratic polynomial. And then number 4, the 4x squared plus 17x plus 15 is also a quadratic polynomial. Nice job, you guys. All right, take a minute and make sure that you have these. I'll save this recording as well as post the PDF on our Advanced Algebra Moodle website. You're welcome to listen to any piece of this recording again on our YouTube channel. In the meantime, you're going to practice with our polynomial assignment number 1. So you're going to work quietly on your polynomial assignment number 1. You may work with another classmate so long as you're quiet and on task. And then make sure that you're checking with the posted answer keys. And then this will be due at the start of next class period. I'm going to go ahead and pause and save the recording now. Nice job today, ladies and gentlemen. Thank you for using this time wisely.